into the world of quantum computing. In the next hour, we will explore the fascinating realm where the rules of classical physics meet the mind-bending principles of quantum mechanics to create a new paradigm in computation. Now, first the definition of quantum computer. A quantum computer that uses the voltage laws of quantum mechanics to perform massively parallel computing through superposition, entanglement, and interference. Whereas in classical computers are considered that we use nowadays, a computer that uses voltage flowing through circuits and gates, which can be controlled and manipulated entirely by classical mechanics. Now, we often think of computers as the devices that power our digital world, but imagine a computer that operates by harnessing the power of subatomic realm, where the laws of physics as we know them begin to blur. That's the essence of quantum computing, a topic that holds the potential to reshape our understanding of computation and solve problems previously thought to be impossible. Now, before we delve into the details of quantum computing, let's take a moment to reflect on the quantum computers that we are familiar with, that is, the classical computers. These devices, which we use every day, process information using bits that can be either 0 or 1, called the binary units. However, imagine a computer where a bit can be both 0 and 1 at the same time. This concept forms the foundation of our exploration today, the quantum bit, or terms at qubit. Now imagine a journey through time where the quantum landscape has transformed from the abstract theory to the concrete technology. Now, in the early 20th century, pioneers like Max Planck and Albert Einstein laid the foundation of quantum mechanics, revolutionizing our understanding of the subatomic world. Concepts like superposition and entanglement emerged, hinting at the potential for the quantum computation. The 1980s witnessed the birth of quantum computing as physicist Richard Feynman proposed the idea of quantum systems to simulate quantum phenomena more efficiently. Now, physicist David Deutsch introduced the concept of quantum Turing machine, the essential step toward the quantum computation theory. The brief history of quantum computers as given the following. Now, in the 1990s, we are discussing on the 1990s saw the progress in quantum algorithms. Peter Shor's algorithm, perfecting large numbers, and Grover's search algorithm demonstrated the vast potential of quantum computations. Now, the researchers began explain the connection between quantum mechanics and computation, laying the groundwork for quantum algorithms. The 2000s marked significant steps in quantum technology. Experimental demonstration of basic quantum gates become possible, showcasing the feasibility of building quantum computers. Early quantum devices, such as ion traps and superconducting qubits, paved the way for practical implementation. Now, in the 2019 witnessed the historic milestone. Google claimed to achieve a quantum supremacy, a moment when a quantum computer perform a task faster than the most advanced classical computers. Now, quantum computing's evolution continues with ongoing research into error correction, fault-tolerant devices, and novel qubit technologies. Now, as we reflect on this evolution, we find ourselves at the threshold of a new era, one where the limits of quantum classical computations are challenged and differentials. The journey is ongoing with each step. Quantum computing brings us closer to unlocking all the full potential of the quantum realm. Now differentiate between the classical and quantum mechanics. In classical mechanics, it deals with the macroscopic particles, whereas in quantum mechanics, it deals with the microscopic particles. In classical mechanics, it is based on Newton's laws of motion and Maxwell's electromagnetic wave theory, whereas quantum mechanics is based on Schrodinger's equation. In Planck's postulate, only discrete value of energy are emitted or absorbed, the origin of quantum. The future state in classical mechanics can be predicted with certainty, whereas in quantum mechanics, it only gives the probabilities of finding particles in various locations. Now, quantum computers, these are now quantum computers that are building today. These are Chinese 76 qubit photon, that is IonQ, 32 qubit quantum computer, and there is IBM 53 qubit supercomputer. These are the quantum computing corporations. These companies are racing amongst ourselves. These are European standards landscape. These are the hardware. Generally, these are the components and materials. These are the operating systems based on quantum computing. These are the applications in different fields, that is chemistry and pharma, security and encryptions. We go through that. Now the question arises, what is a qubit? As in classical computers, the smallest unit is bits, that is 0 or 1. Similarly, in quantum computers, the smallest unit is called qubit. As we know that in classical computers, the information is saved in the form of code. That is a combination of bits, either 0 or 1. This is called binary coding. For example, that my name is Shamikh is coded in binary form is as shown in the screen. Similarly, every information, whether it can be name, photo, audio, video, everything is coded in binary. Classical bit can be 0 or 1 at a time, but a qubit can be a superposition of 0 and 1. Now, what does this means? Now, let's understand with the example of coin. A coin has two sides, heads and tails. Now, assume 0 as heads and 1. Okay. Now, assume 0 as heads and 1 as tails. As we flip a coin, it's either in position 0 or 1. But consider a coin is revolving on its edge. Now it's neither 0 or 1, but is in the superposition of 0 and 1 at the same time. Now this superposition collapses when observed. Now when we observe, this superposition collapses. When in our example of coin, when we observe, the flipping is stopped and shows a definite state of 0 and 1, but until the coin is continuously flipping. This is where the magic happens. Adding qubits increases the power exponentially. If we have 2 qubits in superposition, then there are 4 possible states. Similarly, 3 qubits have 8 states, and so on. In short, n qubits have 2 raised to the power n states, where n bits has only n states in classical computers. Now let's understand the concept of superposition. A qubit in superposition is in both of the states, that is either 1 and 0 at the same time. If this state is measured, we only see one or the other state with some probability. To understand superposition better, let's delve into a famous thought experiment, the Schrodinger's cat scenario. Now imagine a cat in a box. According to quantum mechanics, the cat can exist in superposition of both alive and dead states until observed. Picture the cat in a quantum box. Quantum mechanics suggests that until we open the box and observe, the cat is both alive and dead simultaneously. A puzzling state that captures the essence of superposition. Recall the quantum coin toss analogy. Before catching the coin, it's in a superposition, both heads and tails. This is how quantum computers explore multiple possibilities in parallel. Now, only being in superposition is not enough. Now, there is another concept which is called entanglement. What that makes quantum computer so powerful? When a pair or group of particles is generated, interact, or share spatial proximity in a way such that quantum state of each particle of the pair or group cannot be described independently of the state of the others, even when the particles are separated by a large distance. An entangled pair is a single quantum system in a superposition of equally possible states. The entangled states contains no information about the individual particles, only that they are in opposite states. If the state of one is changed, the state of the other is instantly adjusted to be consistent with the quantum mechanical rules. Irrespective of the distance, time, the two entangled qubits are always correlated to each other. If the measurement is made on one, the other will automatically collapse. Quantum entanglement is at the heart of disparity between classical and quantum physics. Entanglement is a feature of quantum mechanics lacking in classical mechanics. Entanglement is a joint characteristic of two or more particles in a mathematical correlation. Einstein called it a spooky action at a distance because irrespective of distance and time, if two qubits are entangled, they are correlated to each other somehow magically. Now, the applications of quantum entanglement. Quantum entanglement forms a foundation of secure communication. Think of it as a sending secret message using a pair of interlinked walkie-talkies. If one walkie-talkie receives a message, the other instantly decodes it, ensuring secure and instantaneous communication. As we delve into quantum entanglement, remember that it's only just a curiosity. It's a phenomena that has practical implications, from secure communication to the mysterious interconnectedness of particles across the universe at subatomic level only. The 2022 Nobel Prize was given to three researchers, Alain Aspect, John Clauser, and Anton Zellinger, who have discovered that entangled particles behave like a single unit even when they are separated far, far away. For example, one is on Earth and other is on Mars, then the entanglement cannot be broken. They are two particles at the same. Now there is a another concept of interference. As we discussed above, that qubits are in superpositions until they are observed. So when we give a input to a quantum computer, then after computation, the output is in the form of classical bits. This happens with the use of interference. We only need to interfere in such a way that the outcome is what we desired. Imagine two waves in a pond, colliding with each and creating patterns. Some areas with higher waves, others with lower. Quantum interference is somewhat similar, but instead of waves, we are dealing with probabilities of quantum states. Imagine you have a coin in a superposition of both heads and tails. If you flip it multiple times and record the outcomes, you will notice something intriguing. Even though each flip has 50% chance of being heads or tails, the cumulative results won't always be evenly split. They might show streaks of heads or tails. Think of a coin that's slightly heavier on one side. When you flip it many times, you will observe that it doesn't always land evenly between heads and tails. This non-uniform distribution mirrors quantum interference in a way. Quantum interference is at the core of quantum computers. These computers manipulate qubits in such a way that their quantum states interfere constructively to produce the correct result while suppressing the incorrect possibilities. Quantum interference showcases the remarkable nature of quantum mechanics. It's just not a mathematical concept, but a real phenomena with practical applications. From understanding particle behavior to enabling the power of quantum computing. Quick recap before we go further. Now, a superposition, a simple graphical representation of some of the quantum features enabling quantum computing. Superposition is the ability to exist in two different states at the same time, as we discussed. Now, interference refers to the wave properties of adding and subtracting magnitude, which allows state manipulation. And entanglement allows distinct qubits to be bounded together no matter how distant they are. These are the basic three concepts of that are the basic in a quantum computer. Now, how a quantum computer works. For example, a superposition of all the possibilities are given in a qubit. The quantum circuit, then we apply a quantum circuit and different qubits are driven through the interference. Then the solution, the possible, only the required outcome that we generated by the use of interference. Now there is another concept that is called decoherence. Now quantum decoherence is the loss of superposition because of the spontaneous interaction between a quantum system and its environment. Decoherence can be viewed as the loss of information from a system into the environment. The reason why quantum computers still have a long way to go because superpositions and entanglement are very extremely fragile state. Preventing decoherence remains the biggest challenge in building quantum computers. Now, another concept is measurement. If a quantum systems were perfectly isolated, it would maintain a coherence indefinitely, but it would be impossible to manipulate or investigate it. A quantum measure is a decoherence process. When a quantum system is measured, the wave function collapses to a new state according to a probabilistic rule. Now let's start building the foundation of quantum computing by introducing the quantum gates. These are the building blocks of quantum circuits, analogous to the logic gates we encounter in classical computing. However, quantum gates wield the power to manipulate qubits in ways that classical gates only dream of, thanks to the principle of superposition and entanglement. A quantum gate or a quantum logic gate is a basic quantum circuit operation on qubits. They are the building blocks of quantum circuits, like classical logic gates are for conventional digital circuits. The number of qubits in the input and output of the gate must be equal. A gate that acts on n qubit is represented by 2 to the power n by 2 raised to the power n unitary matrix. Unlike many classical logic gates, quantum gates are reversible. That is a unitary matrix. We all know that in linear algebra, a complex square matrix U is unitary if its conjugate transpose U star is also its inverse. Now these are the some gate. The first is poly X gate. It is almost classical NOT gate. Then there is another gate. This is poly Y gate. Then poly Z gate. Then there comes the Hadamard gate. Hadamard gate is different in every aspect. It's a no classical equivalent. This is after qubit in state 0 or 1 has been acted upon a Hadamard gate. The state of the qubit is in equal superposition of 0 and 1. Thus, the qubit goes from a deterministic state to a truly random state. That is, if a qubit is now measured, we will now measure 0 or 1 with equal probability. We see that Hadamard is his Orr's inverse, that is H inverse equal to H, or H square equals to I. Therefore, applying Hadamard twice to a qubit, we change nothing. This is not happening in classical quantum gates. By applying a randomizing operations to a random state produces a deterministic outcome. This is one of the most important gates in quantum computing. There's another gate, the C0 gate. These are the difference gates on quantum and classical ones. We all know the classical gates. These are the quantum gates. There's a poly S gate, poly Y gate, poly Z gate, Hadamard, and different. We will discuss deeply in later somewhere. Now come to the quantum circuits. A quantum circuit is a model for quantum computation in which a computation is a sequence of quantum gates with n qubit registered linked by wires. Similar to that of in classical circuits, a classical circuit is made up of simple logic gates. Similarly, the quantum circuits are made up of simple quantum gates. The circuit has fixed width corresponding to a number of qubit being processed. These are some examples of the quantum gates. Now Bell state. The important is the Bell state. Okay. Using 2 bits to generate an entanglement state, also called a Bell state, with a head mod gate and a CNOT gate. Now, to generate an entanglement state between the 2 qubits, we use a Bell state. That is, with the using of head mod gate and a CNOT gate. Now, uh, as we know, the classical logical circuit, the circuit behavior is governed by explicitly by classical physics. We all know signal states are simply bit vectors. For example, x equals to 0, 1, 0, 1, 1. Then the operations are defined by Boolean algebra. No restriction exists on copying and measuring signals. A small, well-defined set of universal gates, NAND, AND, NOR, NOT, and NOT, etc. Well-developed CAD model. Circuits are easily implemented in fast, scalable, and microscopic technologies such as CMOS. Now, in quantum gates, circuit behavior is governed explicitly by quantum mechanics. Single states are vectors interpreted as superpositions of binary qubits, vector with complex number coefficients. Operations are defined by linear algebra over Hilbert space and can be represented by unitary matrices with complex elements. Severe restriction exists on copying and measuring signals. Many universal gate sets exist, but the best type are not obvious. Circuit must use microscopic technologies that are slow, fragile, and yet not scalable. For example, NMR. Now we come to the quantum algorithms. It may be possible to solve a problem on a quantum system much faster, that is using fewer steps than on a classical computers. Now, Shor's algorithm, Shor's factoring algorithms, and Grover's search algorithm are examples of problem where quantum algorithms are known and are faster than any classical ones. Implications in cryptography and information security is also given by quantum algorithms. Now, what makes a quantum algorithm potentially faster than any classical one? First is quantum parallelism. By using superpositions of quantum gates, the computer is executing the algorithms on all possible input at once. Now, dimension of quantum Hilbert space. The size of the state space for the quantum system is exponentially larger than the corresponding classical system. The third is entanglement capability. Different subsystems, that is qubits, in a quantum computer become entangled, exhibiting non-classical correlations. These are the four famous quantum algorithms: the Fourier transform, Shor's prime factorization, Deuce-Dosha algorithm, and discrete logarithm problems, search algorithms, and quantum simulation. Now, for example, in Shor factorization algorithm, uh, if we factor in classical steps, then the complexity is raised to the power n is to 2 raised to the power n, wherein using Shor's algorithm, it is given is log n, that decreases the time by a large factor. Now, quantum programming. There is already a number of programming languages adapted for quantum computing. The purpose of quantum programming languages is to provide a tool for researchers, not a tool for programmers till now. A QCL is an example of such a language. IBM Qiskit is also a platform uh, that we use. The QCL is an example of QCL. A simple program is written. This is the screenshot from the Qiskit program in which we can build our own circuits and gates. These are the programming languages that are currently in use and are developing. Now, how does a quantum computer work? Now, nowadays, from our classical computers, for example, let's consider IBM's computer. We want to simulate some problem on IBM computer. Then we submit a job from our classical computer that we use nowadays through cloud into the servers of IBM. The servers translate quantum circuits and execute on the quantum computer. Now, the possible solution is given back to the servers, and then it is uh, come in classical form in our computer, that in the form of 0 or 1. These are the some applications of quantum computers in travel and logistics, chemistry, pharmacology, climate modeling, financial analysis, and cryptography. Uh, Quantum computer is also very well used in AI, developing of AI, big data, and data mining, especially in data mining. Now, we consider about post-quantum world. When the quantum computers arrives, there is a good chance that quantum computers will be able to crack a RSA 20 period within 5-10 years that needed about 8,000 qubits in a universal computer to do this. Some encrypted data has a shelf life of more than 10 years. It may take 10 years to cut over a new encryption scheme, so companies or governments are scrambling to figure out what to do. Most encryptions used today is not safe in quantum world. If someone has been recording a HTTPS session, say they may not be able to decrypt it. But a few years from now, who knows? There are encryption algorithms that are safe. Secure communications will move to symmetric encryptions or hash algorithms, or have perhaps latest algorithms. The quantum key distribution will likely be more popular for most sensitive communications. Some governments and banks are already starting to use quantum safe algorithms, and this is expected to increase over the next few years. So the features of quantum computers, these are the given by the features. As we see in the graph, the qubits in computers in the last 4 years has been increased drastically. Uh, for example, now the problems with quantum computers. First problem is of decoherence, as we discussed earlier. A quantum system is extremely sensitive to external environment, so it should be safely isolated. It is hard to achieve the decoherence time that is more than the algorithm running time. The other problem is error corrections. The other is physical implementation of computations. The other is new quantum algorithms to solve more problems. Entangled states for data transfer. The running time increases exponentially with the matrix size. This is the IBM's IBM Q quantum computer. This is the highlighted part is at the heart, where the qubits are stored in a form, and above this full computer is had kept in a chamber which has absolute zero temperature, that is minus 273 degrees Celsius, to maintain the superposition and entanglement states. Career aspects in quantum, whereas there are various career roles in quantum computing currently now in IBM and various other companies also. I also only consider the IBM. There is the research field, the quantum, and the software development and hardware development. These are the some references which I used to study. That is, you can also go through it. That is a quantum computing for computer scientists. Is a Microsoft research free video on YouTube. The other is quantum computing in 21st century by David Jemison. The Royal Institutions by Royal Institutions. You can also go through the Qiskit. You can implement some gates. Thank you.
Thanks a lot, dear Shamikh, for this very interesting session on quantum. So do we have any questions from the audience? We can take up any discussion or questions now.
I do have one question.
Yeah, please.
I'm audible.
Yes, yes.
Yes, Assalamu alaikum, sir.
Salam.
Like, I want to know, like, regarding quantum computing, if you are starting a career, if you have done some, learned some Java language or something in IT or cloud.
Yes,
So,
yes.
in getting into quantum computing in development, like, what will be the software roles and what will be the, like, roadmap so that
Uh,
we can.
yeah, as I show earlier, let me show you that these are the quantum programming languages. Okay, these languages use that the languages that we use nowadays. For example, you consider Java. Okay, uh, then we know the Qiskit.js is also a program that runs on JavaScript, and majorly all the languages use Python as first to code, but by using these languages, we can program in quantum computing.
If we
Okay, any other
apply,
question?
yes, if we apply for a initial fresher role for quantum computing in any company, suppose IBM, so
Okay,
like
okay.
basically what will they test? Does they require any experience or like they can take fresher as?
No, it always for any fresher, any company will always test for your programming skill, irrespective of your languages. Okay, for example, if you know Python, then uh, initially they check your problem solving skills and the language you follow. After that, you can implement your language on the quantum computers and quantum simulations tools.
Yes. So the knowledge of cloud technology like AWS, it will be
Okay.
also helpful for this thing. Like I have done
uh,
AWS.
the cloud knowledge is uh, now let's see, everything in nowadays is running on cloud. Okay, everyone working on a quantum computer, that is for example IBM's quantum computer, is not possible. So everyone must have to go through cloud to simulate their problems, and in order to get in classical world, the answer in classical world, we must uh, simulate through the cloud. Getting what I'm trying to say.
Yes, basically we should go through cloud main thing.
Yeah, currently.
Like all the like major MNCs are utilizing cloud only, like they are moving their applications and web apps on cloud only, I think so.
Yes, yes, sir. Currently, the quantum is only working through cloud. It's not commercially available. Any other doubt?
Mainly in quantum computing, like initially which company initiated a start is IBM only, I think so.
Sorry, I can't hear.
The company which started basically from scratch in quantum computing first is IBM, I think so.
No, currently, uh, basically the first companies to start is a Chinese company, and then after that Google follows. Then next, then after the all the major giants like IBM and other are involving. First major initiative is but taken by the Google.
In data centers also, I think the mainly the utilization of quantum computing concept is also there.
Uh, maybe I think so. That I can't say. Any other?
Basically, to have a good command over the programming languages, and then we can go from some online courses or like offline courses to get into this.
Yeah, exactly. There is also a platform by IBM, that is Quantum Cascade, and Quantum simulation tools are given, and that you can try and train yourself according to it. You want go through the Quantum Cascade program, IBM Cascade.
Is there any question from Dr. Dilshad Begum? Okay, so any other question? Whoever has any point to discuss, they can unmute themselves.
Yeah, like as the presenter of the webinar
Yeah.
who has presented this presentation, I think sir is working as a research.
Yes.
As a researcher in some foreign university.
Okay.
Any other question anyone has? We can take few more questions. Someone wants to ask something or know something more. So if there are no further questions, maybe we can close this session. So Shamikh, can we close now?
Yeah, okay.
Okay, thanks everyone for joining this webinar on this exciting technology on quantum. So thanks a lot, and with this we close this session. Thanks everyone, and Jazakumullah khair, Shamikh.
Okay, thank you.